Assalamualaikum and good day. In this video, I will explain how to find the dual of any LP and the relation that exists between an LP and its dual. When taking the dual of a given LP, we refer to the given LP as the primal. Another related linear program to the primal is called the dual. If the primal is a maximum problem, then the dual will be a minimum problem, and vice versa. For convenience, we define the variables for the primal LP to be Z, X1, X2 until Xn, and variables for the dual LP to be W, Y1, Y2 until Ym. These are general rules for constructing the dual problem. If the original problem is a maximum problem, then the dual is a minimum model. And if the original problem is a minimum model, then the dual is a maximum problem. Let us write this important information in a table. As I mentioned before, variables involved in primal LP are Z, X1, X2 until Xm. Z, X1, X2 until Xn. And in dual, we use W, Y1, Y2 until Ym. Okay. If the objective function of the primal is to maximize Z, therefore, the objective function of the dual will be minimize W. And if the problem is to minimize Z, therefore, the objective function of the dual is to maximize W. Next, the number of variables in the dual equals to the number of constraints in the primal. Okay, we write this information in this table. The number of variables in the dual equals to the number of constraints in the primal, while the number of constraints in the dual equals to the number of variables in the primal. Okay. For example, in the primal, we have M constraint. Therefore, in the dual, we have M variables. And if in the primal has N variables, and therefore in the dual there are N constraints. Next, the coefficient of the objective function in the dual problem come from the right hand side of the original problem. Okay, coefficient of the objective function in the dual come from the right hand side of the primal, and the right hand side of the dual come from the coefficient of the objective function in the primal. And the last one, the coefficient of the first constraint function for the dual problem are the coefficient of the first variable in the constraint for the original problem, and similarly for other constraints. This means that in the primal, let's say we have 3 constraints. We have constraint 1, constraint 2, and constraint 3. Okay, so the coefficient of the first variable in the constraint, we have the first variable in the primal is x1. So let's say the coefficient of the x1 in the first constraint is a11 plus a12 times x2 time plus a13 x3 and so on, less than or equals to right hand side, for example. Okay, and for the second constraint, we have a21 x1 plus a22 x2 plus a23 x3 plus until xn less than or equals to right hand side. Okay, the third constraint has a31 x1 plus a32 x2 plus a33 x3 plus until xn less than or equals to right hand side. This is the example. Okay, so the coefficient of the first variable becomes the coefficient of the first constraint in the dual. Okay, let's say in the dual, the first constraint will have a11 y1 plus a21 y2 plus a31 y3, and then the sign of the constraint and the right hand side, maybe the sign is less than or equals to. This is example. Okay, means that from here we can see the coefficient of the first variable in the primal becomes the coefficient of the constraint of the variables in the first constraint. Okay. Okay. It also shows that the second dual constraint correspond to the second variable in the primal, mean x2, and the third constraint in the dual correspond to the third variable, which is x3 in the primal. This table shows how to write the sign of constraint and variable in the dual LP. The sign of the variable in the dual LP depends on the sign of the constraint in the primal. It is also clear that the dual constraint correspond to the primal variable. For example, to write the sign restriction of the dual of a maximum problem, dual of the maximum problem, if the primal constraint is greater than or equal to constraint, then the corresponding dual variable yi is less than or equals to 0. If the primal constraint is an equality constraint, then the dual variable is now unrestricted in sign, or known as URS. If the primal variable is less than or equal to 0, then the dual constraint will be less than or equal to constraint. But if the variable is URS, then the dual constraint will be an equality constraint. We begin by explaining how to find the dual of a maximum problem, in which all variables are required to be non-negative and all constraints are less than or equal to constraints. This LP is called a normal maximum problem. A normal maximum problem may be written as a model in example 3.8. We have a maximum Z equals to 60x1 plus 30x2 plus 20x3 with these three constraints. All constraints are less than or equal to constraints, and all variables are non-negative. Let us find the dual of this LP. The primal LP has three variables and three constraints, and the objective is to maximize Z. Therefore, from this information, we can know the dual, the number of variables and constraints in the dual. Okay, the number of variables equals to the number of constraints in the duals. Therefore, the dual of this LP has three constraints and also three variables. And the objective of this dual LP is to minimize W. Okay, now let's write the model. The objective of the dual LP is minimize W equals to, we have three variables, so we write the variable first, y1, y2, y3 subject to three constraints. So we just write the variables of every constraint, y1, y2, y3. We have three constraints. Now let's fill in the coefficient in the objective function. The coefficient of the objective function in the dual LP come from the right hand side of the primal. Therefore, we have minimize W equals to 48 y1 plus 20 y2 plus 8 y3. And the right hand side of the constraint in the dual come from the objective coefficient. Okay, we have the right hand side of the first constraint is 60. 30 is the right hand side of the second constraint, and we have 20 as the right hand side of the third constraint. Now let's fill in the coefficient in the left hand side of every constraint. The coefficient in the first constraint come from the coefficient of the first variable in the primal. Okay. The first variable in the primal is x1. So we take the coefficient of this variable in every constraint. Therefore, we have 8y1 plus 4y2 plus 2y3. And the coefficient in the second constraint come from the coefficient of the second variable in the primal, which is x2. Thus, we have 6y1 plus 2y2 plus 3/2y3. And for the last constraint, we take the coefficient of the last variable in the primal. Therefore, we have 1y1 plus 3/2y2 plus 1/2y3. Okay, now let's get the sign of the constraint. Okay, the sign of the constraint in the dual depends on the sign of the variable in the primal. Okay, we can see all variables in the primal are non-negative. All variables in the primal are non-negative. So these variables satisfy the normal maximum. Therefore, the sign of the constraint in the dual also satisfies normal minimum. What is the sign for the normal minimum? The sign is greater than or equal to. Then, we need to find the sign for every variable in the dual. Okay, the sign of the variable in the dual depends on the sign of the constraint in the primal. As we can see in the primal LP, all constraints have less than or equal to sign. This sign is sign for normal maximum. This sign satisfies the normal maximum problem. Therefore, all variables in the dual also satisfy the normal minimum problem. Means all variables are non-negative. So we have y1, y2 and y3 are greater than or equals to 0. When a minimum problem has all greater than or equal to constraint and all variables are non-negative, this LP is called normal minimum problem. When the primal is normal maximum problem, we will get a normal minimum problem as a dual. Many LPs are not normal maximum or normal minimum problems. Some LP may contain greater than or equal to constraints for maximum problem or less than or equal to constraint for minimum problem, or maybe it has an equality constraint or unrestricted in sign variables. For non-normal problem, let's discuss example 3.9. This LP this LP has two variables and three constraints, and the given LP is a maximum problem. Now for the dual, it has two constraints, and the number of constraints is come from the number of variables in the dual come from the number of constraints. Therefore, the dual has three variables, and the objective of the dual is to minimize W. Now let's write the model. Minimize W equals to, okay, we write down the variables involved in the dual, which is Y1, Y2 and Y3, subject to two constraints. So we have Y1, Y2 and Y3, Y1, Y2, Y3. And then this one is for the sign restriction. Okay, let's fill in the coefficient of the objective function. The right hand side of the primal represent the coefficient in the objective function of the dual. So we have 2y1 plus 3y2 plus 1y3, and the right hand side of the constraint in the dual come from the objective function, the coefficient in the objective function of the primal. So we have 2 and 1. Now for the left hand side of the constraint, the coefficient of the first constraint is 1, 2, 1. 1y1 plus 2y2 plus 1y3. And for the second constraint, the coefficient come from the coefficient of the coefficient of the second variables in the primal. So the second variables in the primal has coefficient 1 in the first constraint, negative 1 in the second constraint, and negative 1 in the third constraint. So we write 1y1 minus 1y2 minus 1y3. Okay, now let's get the sign of the constraint. The sign of the first constraint comes from the sign of the first variable. Okay, the first variable, which is x1, is a non-negative variable. Non-negative variable satisfies the requirement of the normal problem. Therefore, the sign of the first constraint also satisfies the sign of normal minimum problem. The sign of the normal minimum problem is greater than or equal to. And for the second constraint, we refer to the sign of the second variable in the primal. Since the second variable is URS, therefore the second constraint is an equality constraint. Lastly, we get the sign for every variable in the dual. The sign of y1 depends on the sign of the first constraint in the primal. The first constraint in the primal is an equality constraint. Therefore, y1 is URS. y2 is, okay, since the second constraint is greater than or equal to constraint, where this sign is not signed for normal maximum, therefore the variable also not normal, which is less than or equal to 0. And y3, the sign of the third constraint depends on the sign of the sign of the third variable depends on the sign of the third constraint in the primal. This is less than or equal to constraint. This sign is signed for normal maximum. Therefore, the variable is a normal variable. Now we already complete the dual of the given LP. Let us discuss another example. We have a minimum problem with 3 variables and 4 constraints. Therefore, for the dual, the objective is to maximize W. 3 constraints involved in this model and 4 variables. The complete model of the dual is maximize W equals to y1, y2, y3 and y4. Okay, the coefficient of this objective function is equal to the right hand side of the primal. So 2y1 plus 1y2 plus 1y3 plus 3y4. Subject to, we have 3 constraints. Better we write down the variables in every constraint: y1, y2, y3 and y4. And the sign restriction Okay, now let's write the right hand side of the first constraint. The right hand side of the first constraint is 2, second constraint is 4, and 6 is the right hand side of the third constraint. And the coefficient of the first constraint in the dual is 1, y1 plus 1y2 plus 0y3, because there is no x1 in the third constraint, plus 2y4. And the second constraint is 2y1 plus 0y2 plus 1y3 plus 1y4. And for the last constraint, the coefficient comes from the coefficient of the third variable in the primal. Okay, the coefficient is 1, -1, positive 1 and 0. Okay, now let's write the sign of the first constraint. Okay, the sign of the first constraint depends on the sign of the first variable. The first variable is URS, so therefore the sign of the first constraint is equal. Now the sign for the second and the third constraint depends on the second and the third variables in the primal. Since both variables are non-negative, which is satisfied the normal problem, therefore the sign of the second and the third constraint in the dual also satisfy the normal maximum problem. The sign of the normal maximum problem is less than or equal to. You almost complete the model. Okay, the last one is to get the sign of every variable in the primal. In the dual. Okay, y1, the sign of y1 depends on the sign of the first constraint. The first constraint is greater than or equal to constraint, which is the sign for normal maximum. Therefore, this variable also a normal variable. Now for y2, look at the sign of the second constraint in the primal. The sign is greater than or equal to. This also a sign for normal minimum problem. Therefore, this variable is a normal variable. y3 is URS and y4 is non-positive variable. Since the sign of the last constraint is less than or equal to, which is not the sign for normal minimum, therefore the variable is not a normal variable. We can find the optimal value solution from the optimal primal tableau. The value of the dual variable yi depends on the sign of the primal ith constraint. If the ith constraint is less than or equal to constraint, then the value of yi is equal to the coefficient of Si in the row 0 of optimal primal tableau. If the sign of the I primal constraint is greater than or equal to, then yi is the coefficient of ei times negative. And if the I constraint is an equality constraint, then yi is equal to coefficient of ai, then minus m if the primal is a maximum problem, or plus m if the primal is a minimum problem. Now let us discuss example 3.11 and 3.12. Given this LP and the optimal tableau. Okay, before we find the value of the dual variable, let us write the dual LP. This is primal and the dual is minimize W equals to 15y1 plus 5y2 plus 10y3 subject to 1y1 plus 0y2 plus 2y3, and the right hand side is 3. The second constraint is 3y1 plus 2y2 plus y3, and the right hand side is 2. And the last constraint is 2y1 minus y2 minus 5y3. Right hand side is 5. Okay, the sign of the first constraint is, okay, let's look at the sign of the variable in the primal. All variables are non-negative. This is a normal variable. Therefore, the sign of the constraint are the sign of the normal minimum problem, which is greater than or equal to. Now, let's write the sign of y1, y2, and y3. y1, okay, let's refer to the sign of the first constraint. The sign of the first constraint is less than or equal to. This is the sign for normal maximum problem. Therefore, this variable is a normal variable. y2 is not normal because the sign of the second constraint is greater than or equal to. And the last one, y3, is URS. Okay, now let's get the value for y1, y2, y3, and w. We know that y1 corresponds to the first constraint in the primal. Since the first constraint is less than or equal to, therefore y1 is equal to the coefficient of S1. Okay, in row 0. Okay, the value of the optimal, the value of the variable in the dual, okay, we just can get it from the optimal tableau of the primal. The value of the dual come from the row 0 of the optimal primal tableau. Just refer to this row 0. Okay, now the value of y2 depends on the second constraint of the primal. Okay, since the second constraint is greater than or equal to constraint, therefore y2 is equal to the coefficient of E2 times negative. So this is value for y2, but we need to multiply by negative. And for y3 correspond to the third constraint in the primal. Okay, the third constraint is an equality constraint. Therefore, y3 is equal to the coefficient of A3 then minus m. Okay, because we need to eliminate the m. Okay, now let's write the value for y1, y2, and y3. So y1 is equal to coefficient of S1 in optimal row 0, which is 51/23. y2 is equal to coefficient of E2 in row 0 times negative. So y2 is equal to 58, negative 58/23. And y3 is equals to coefficient of A3 minus M. Y3 is equal to 9/23. And last, W is equal to the optimal value of the primal, which is Z, equals to 555/23. This value. Okay. Let us do this next example. Given this LP and its optimal tableau, we get the value of the variable in the dual from optimal row 0. Okay, let's write the dual LP. We have a maximum problem equals to 4y1 plus 2y2 plus 6y3 subject to 1y1 plus 0y2 plus 1y3, and the right hand side is 3. For the second constraint, we have 1y1 plus 1y2 plus 1y3, and the right hand side is 2. The last constraint, we have y1 minus y2 plus 2y3, and the right hand side of this constraint is 1. Okay, the sign of the first constraint is, okay, let's look at the sign of the first variable in the primal. The first variable is non-negative, which is a normal variable for normal minimum problem. Therefore, the sign of the first constraint also the sign for the normal maximum problem, which is less than or equal to. Same goes to the second constraint. Let's refer to the second variable. Okay, we can see that all variables are non-negative, okay, which is a normal variable. Therefore, we have a sign for normal maximum problem. Okay, the second constraint is less than or equal to constraint. Same to the third constraint. Okay, now let's write the sign for the first variable in the dual. Okay, since the first constraint is greater than or equal to constraint, which is the sign for normal minimum, therefore the variable is also a normal variable. Okay, y2, this is not the sign for normal minimum, therefore y2 also not a normal variable. y2 is less than or equals to 0, and y3 is URS. Now let's get the value for y1, y2 and y3. Okay, y1 correspond to the first constraint in the primal. Okay, the sign of the first constraint is greater than or equal to. Therefore, y1 is equal to the coefficient of E1 times negative. So this is the value for y1. So but we need to times by negative. with negative. Next, y2. We have the second constraint in the primal is less than or equal to. So we need to find the coefficient of S2 in the optimal row 0. So y2 is equals to 0. And y3 is the coefficient of A3 plus M. So this is y2 and this is y3. Okay? Let's write the value for every variable. Y1 is equal to coefficient of E1 times negative, we get 3. Y2 is equal to 0. And y3 is equal to negative 1. And W is equal to Z equals to 6. That's all about the dual problem. Thank you.